Hey everyone, it's March 21st, 2022. We are in the spring semester for statistics at College of Sequoias. I'm Professor David Jones, and today we're starting to look at inferential statistics in Chapter 9. So let's start our drawings. Chapter 9 is on inferential statistics. And what do we mean by that? So inferential statistics is the process of trying to infer something about the general population based on some data, obtained from a sample, obtained or collected from a sample. This is the whole point of why we sample. This is why we do statistics right here. This is where we're getting down to the nitty and gritty. What's the point? Probability is like, it's nice, it's related to statistics, but when you hear statistics and you hear about it in the news, this is what they're doing. And when I say infer, maybe I'll underline it in a different color there. Inferring or inference is making an assumption. And hopefully a reliable assumption. Okay. So in 9.1, which is where we're starting, 9.1 is going to be on population proportions. So let's just bring some stuff that's relevant to the world. Let's talk about relevant stuff. Actually, I should give you a little bit longer to write that down if you're writing stuff down. I can tell you what, since we are still in the pandemic, I've been looking at COVID-19, the proportion of death to cases. Now, I guess that's a little morbid. I should probably have done proportion of people that lived. But that's not the scary part. And so people aren't like, they're less interested in stats that aren't scary. That's just truth. So let's just look at California. California, we have had deaths is currently at, this is updated for today, 87,485, and total cases has been 8,465,358. Now, this includes data from before vaccinations and after vaccinations. So it doesn't show like the effectiveness of vaccinations. But per se, but it does show us like what it does lead to the topic that we're looking into. When we do proportions, remember proportions, we do successes over total. And so if we consider death a success, that's some dark shit right there, right? That's pretty dark. But still, in terms of what we're looking at, the death rate, it works. And so I'm going to just, in my calculator, calculate that. 87,465 divided by that 8 million figure. And I am getting 0.010332, which is 1.0332%. Now, back when the pandemic started, I can tell you in 2020, in March of 2020, I should say, at the end of March, right after it was global, the global rate was 4.71%. So it's gone down since the pandemic started, and that's your vaccinations kicking in, stuff like that. But let's take a look at some other places. That's just California. So this is pandemic death rates by country. Maybe I'll make that a little bit bigger for now while I do it, and then we'll use StatCrunch when we need to. If we look at like, where's one that's got a low number of deaths? There's one in here I really liked. New Zealand, because New Zealand and the Australia region, they have a low population compared to other places. But let's look at like New Zealand. So this was California's. Let me make a note of that. California was 1.03%. And if I look at New Zealand, New Zealand has 163 deaths. Over 497,731. Throw that in a calculator. I am getting 0.0003275. So in terms of like a percentage, New Zealand is at 0.03%. 0.03%. California was at 1.03%. Are either of us like matching the global? Are we matching the global rate? They've got the world rate up here. So we can take a look at the world, like if we collected all the data throughout the world. So globally, since the pandemic started, 6 million deaths. Good God, it's insane. That's a lot of people from just one little thing. And let's throw that bad boy in the calculator. 6,077,582 divided by 470,737,068 cases. And I'm getting 0.0129. So globally, we're looking at 0.129%. So we might look at it and say California's pretty close to globally. New Zealand is not. It's quite a ways away. If you think about how much like how big these sample sizes are. Because remember, when we talked about the law of large numbers, the bigger the sample size, the less the effect each one has. So just adding, like if I add one more case, positive case to New Zealand, and I said 164, you can't see what I'm writing. My bad. So I was doing the calculations for California, New Zealand, and globally.
Did you go up a little bit?
Like that?
Oh yeah, that's fine.
Yeah, let me pause for a second, let you guys get caught up. Need longer?
Oh no, I'm good.
All good, okay. So like, even if we added one to New Zealand, I'm just gonna show real quick. I added one death and one case. So we just had one more result. It's 164 over 497, 732. I get 0.0003294. And even if I write that as a percentage, it's still 0.03. I haven't moved the needle. That's what law of large numbers is. As we get larger, and it stops affecting it. You need a lot to change to make it affect it. So is any of these right? Well, globally is probably the closest thing we got. That's got the most data, the most results, including everybody. So it eliminates factors like precautions California took that, and New Zealand took that other places did not take. New Zealand took a lot of precautions. Everybody had to stay home. Lots of stuff going on over there. But look how few lives they've lost. They've lost 163 people since the pandemic started. That's it. That's crazy. What's the population in New Zealand? $4.8 million, almost 5 million. They've lost 163 since the pandemic started. That's insane. It's super low. So they took some precautions that made a difference, a real difference. Which one of these is right though? Globally is probably the closest, but usually when we're trying to find something out, usually we don't have access to global results. Or even state results, country results, even getting a county's results is high. And this is a special case with the pandemic. But so what? We don't normally have access to the global results. So knowing the true proportion of a scenario isn't easy to find. So we use samples to try to determine that, the true proportion. And you'll notice my California did not match my global. And if you look at US, I didn't do the calculation, but I can tell you what US's was. US had 1.22% as of today. So that's really close. But that's again, that's collecting results from, let's see, US had 79 million, 80 million effectively results, 79.7 million cases. So that's a lot of cases. It's easier to gather the data. The data was collected because it was a global pandemic and it mattered to save lives. Generally, we don't have that. What if I wanted to say, let's see, how many students use Snapchat? Let's do something simpler. How many students use Snapchat? Or let's say, or the proportion of students, because that's probably a better question. Now, I will admit, I totally made these numbers up that I'm about to use. I have no idea if they're accurate. I made them up to present an example. Let's say we asked 250 people. And 140, not people, students. I want to narrow it down to students. And 145 said they use Snapchat. I guess it's capitalized because it is a business, huh? Eraser. So if I do a proportion here, I have 145 users over 250. And if you throw that into a calculator, this is 0.58 or 58%. I'm going to use this to estimate the US proportion of students that do it. And since we're using it as an estimate, we're trying to infer something about the US population. We call this a point estimate. We talked about this in the last class. This is a point estimate, and we call it p hat. Now, how likely is it that it's 0.58? Like, let's say I had a number line from 0 to 1. Here's 0.5. Maybe we'll do 3, 4. I didn't break those down very evenly over here on the left. Let's see if we can make that look a little bit better. 1, 2, 3, 4. There we go. And our 0.58 is right here. That's my 0.58. Well, we already showed with the pandemic info that it may not be right. So maybe we want to capture, like, we want to say, well, it's somewhere in like a range around this set. We want to say it's in an interval. So we aren't confident that we have the correct answer, and we likely don't. In fact, it's borderline impossible that we have the exact percentage. So we want to use an interval around that amount. Around that number. And I can tell you right now, with 100% confidence, the proportion of Snapchat users is the true proportion of Snapchat users I almost abbreviated it SC, but that's what I use for StatCrunch. Who are students is between 0 and 1. I am 100% sure if I start at this end and go to this end, 0% to 100%, I'm 100% sure I've got the right range. It's in there. That's absolutely useless information. I bet I could say to make the same claim if I did like 10% to 90%. If I did like 10% to 90%, I could say the same thing. I doubt it's under 10%, and I doubt it's over 90%. But that's, again, not useful information. What if I wanted to say, like, it's 0.58? What if I wanted to say it's between like 0.55 and 0.61? Well, now I'm a lot less confident. I'm a lot less confident. You know, it's a small window. I'm gonna go, I'd say maybe I don't know, 20% confident. Like, it might be in that range. The true proportion might be in that range. It might be 0.579, and I might have gotten really close to it. So how do we go about doing it? Checking and figuring all this stuff out. We want to give a range. So objective. Give a range that's narrow enough, or interval that is narrow enough that is useful, but not so narrow that it's unreliable. That is what we're doing with statistics. We want to get a range or an interval that is narrow enough that's useful, but not so narrow that's unreliable. And we had 0.58. If I said it was 0.579 to 0.581, it's 0% reliable that it's that small. That is such a small window. It'd be great if it was useful, but it's so small that it's not useful. And so, continue. I've been kind of throwing out numbers there, but based on our sample size, n and proportion and our point estimate p hat, we can numerically come up with these values with a range that has high confidence. And that's what we're going to do today. And this is called a confidence interval. That range is called a confidence interval. Okay. Now to do that, we want to make sure that our data is normal or has the bell curve look. And we talked about last time how to do that. We had said for p hat, we had two criteria. N times p times 1 minus p needed to be greater than or equal to 10. And n had, oops, wrong n. I need the lowercase n here. And n has to be less than or equal to 5% of the population. Those were our requirements. So those are our requirements. And when we had that, we ended up with our mean if we have a normal distribution, we have a mean and a standard deviation. This was just P and sigma for P hat, or our point estimate, was P times 1 minus P divided by N, and then you take the square root. So this is what applicable if those requirements are met. I'm just reminding you of that. We're going to use it in a second. But I thought I would give you, let me pause and let you write it down. What do I mean by being confident that my interval contains the true proportion? I'm going to show you a simulation in StatCrunch. If we can simulate samples in StatCrunch. We're going to use applets and then confidence interval. And I'm going to show you and explain to you what it means. So I'm going to come over here. We go narrow this down a little bit more. Widen that a little bit up. Applets, confidence intervals. And we're going to do a proportion today. We were looking at, for the scenario I completely fabricated, we had a proportion that was 0.58. And I want to have a confidence level of 0.95, which would be 95%. So that's what my simulation is going to be. Simulate the 0.58 or 58% and find intervals with 95% confidence. Let's go with, I'm going to start with n equals 100. Let's do a sample size of 100. Quick compute. I might have to make this bigger. Can I squeeze that down? No, I can't. All right, so we'll have to use it like this for now. So the computer goes and randomly applies this proportion and like basically rolls and goes, did we hit that number or not? Or what numbers did we hit? And like, if I look at like line 85, the results they had an upper limit of 0.463 and a lower limit of 0.657. So I'm going to write this down over here just because I'm going to use it to illustrate something. Line 85, it's got a lower limit of 0.463 and an upper limit of 0.657. Okay. And if you do this same simulation on yours, you're going to get different results. If I click it again, it's going to completely change it. So this is not really reproducible. Where is line 85? Hard to tell. That one? I don't know. If I click on 84, it's red. 24 on mine, it's got a lower limit that says 0.372 and an upper limit that says 0.568. And I'm getting that right there. And so I want to show you pictorially what's going on here. So pictorially, what's going on? So I've got a number line. All right, so, and we had our point estimate was 0.58, which is right about there. So one data set, I'll do the 85 first. It had a lower limit of 0.463, which is about there, and an upper limit of 0.657, which is right about there. Why is it? Huh, okay, must be right. So if I had a bell curve here, This was giving me 95% confidence, which is like 2 standard deviations. And the 0.58 fell within it. The 0.58 fell within the 2 deviations. And then if I come over and I do the other one, line 84, I'll do in pink. It went to, oh, maybe not do pink. Let's do yellow, because pink is the target number on the 9th line. So we're gonna do yellow for this one. 0.463, or I'm sorry, 0.372. This is 0.4, 0.372 is over here. And 0.568 is right here. So if I do its confidence interval, its 95% region is right here. And notice 0.58 isn't in it. So these are 2 samples that were generated by StatCrunch. And if I had done just this latter sample, if this was the only people I polled, and 0.58 was the actual number, is the true proportion, if it was, then that sample didn't capture it. And my study is going to be wrong. It doesn't actually have the true proportion in it. It could be wrong, which is what makes statistics frustrating for a lot of people. It doesn't guarantee a correct answer. The only way to guarantee a correct answer is to have this really high confidence interval. We need like 99.9% confidence. 100% is even better, but 100% is like doing the whole number line. Okay. That's why we're going after this. So how did the computer get these numbers? For the upper limit and lower limit. I guess I should write in there what that means, upper limit and lower limit. It's all based on that percentage of area they want to capture. I don't need to make it all. Let's make it shorter so I can write next to it. If we have a normal distribution, that confidence interval percentage is tied to the area between the limits on a normal curve. So 95% is one width. If I want to be more confident, I could extend it outward. Maybe that's 99%. I've made that window bigger, so there's a greater chance that the true proportion lies in it. And if I made it smaller, maybe that's only 90%. So I'm less confident, but my number range is tighter. So a narrower number or narrower interval means less confident. And a wider interval means more confident. For 95%, a 95% confidence interval, which I'm going to start calling CI. "95 out of 100 samples should contain it." And I'm gonna go back to that applet over here and take a look at it, show you something. All of the green ones on this picture contain it. All of the red ones do not. And it actually tells us at the top whether it contains it or not. 93 contains P. 93 different samples of 100 contained P. And so that's a proportion of 93%. If I reset it and did another 100 intervals, I got 93 again, but it's a different 93. Like 84 is not red anymore. I can reset it and run it again. Why does it keep giving me 90? 93 is a coincidence. Reset, run again. This time it had 98 of them contained it. So usually you do enough of these, the average is 95 out of 100 contain it. So this means, oh shit. So it's not an exact science. Statistics is not an exact science. We don't get exact answers usually. But we've perfected estimating it. Well, come close to perfecting. There's probably always room for improvement. Perfecting how to get an estimate from a sample. Okay. And so I told you this percentage is tied to the bell curve. So other things we've used that were bell curve related, think about the empirical rule. Plus or minus 1 deviation captured 68%. Plus or minus 2 deviations captures 95%. Plus or minus 3 deviations captures 99.7%. That's the empirical rule. It's not exact though. This isn't what we want to use for. This isn't what we use to make calculations. This is more for just eyeballing it or estimating without any work. Now, no one ever wants to be 68% confident, okay? 68% confident is garbage. That means you're wrong 1 out of 3 times. 68% is a failing grade in any class that you take. D's are failing grades. 68% is a D, and that's a failing grade. It may count as a pass, but you're not gonna you can't take the next course, things like that. So what kind of percentage ranges do we look for? We look for like, hopefully 90% or higher. So like, let me give you some numbers for 90%, 95%, 99%. 95%, our estimate of plus or minus 2 is sigma is wrong. It's actually plus or minus 1.96 sigma, which is why we use 2. 2 is easier to remember. But when you're actually calculating stuff to find a confidence interval and do these hypothesis tests that we're going to start doing, that's the value we use. If we want 90%, it's plus or minus that 1 point, it's 1.645 times the standard deviation. And if we want 99%, it's plus or minus 2.575 deviations. This is worth memorizing. It really is. Both of them are worth memorizing. But this is when you're doing the computations. Are you going to be tested on knowing whether or not you know the 1.645, 2.575? No. But it is handy to at least have them on hand, and so you know what you're looking at. So how did they do that? How did they come up with the ranges for what we have? Can I come up with a confidence interval? Let's come up with a confidence interval for our example. For our Snapchat example. My target estimate was 0.58. And that came from 145 out of 250. Recall, the mean of a proportion is equal to that rate. So this is actually my mean. Mean is 0.58. Now standard deviation. Okay, we got some work. So this is calculator work. It was P times 1 minus P over N, and then we take the square root. For us, that's 0.58 times 1 minus 0.58 divided by 250, and then we take the square root. If I do 0.58 times 1 minus 0.58 divided by 250, I get inside my square root 0.000974, and that's as many calculations as my decimal places as my calculator shows. And if I take the square root of that number, I get all the numbers that it lists are 0.3121538. It's got more numbers, so this is like really an approximation. That's pretty close, but let's just go with 4 decimal places. Oh shit, let's go with 3 decimal places. If I round that, that's 0.031. Okay. So that's my sigma. So if I want to get this 95%, I need that 1.96 sigma for 95%. So let me figure out what that is based on that 0.031. 1.96 times 0.031 equals 0.031. And if I do a number line, I won't go all the way to 1 and 0. I think that's taking away from the visualization here. So I'll just go a little bit away. My 0.58, my fingers are tingling from squeezing on the damn pin so much. My 0.58 is right about here. And if I add, that's my 0.58. If I add 0.06076 to that, I get 0.64 0.076 right there. And if I go the other direction, if I do 0.58 minus it, I'm getting 0.512 or 519. That region right there. So 51.9% to 64.1%. That's my 95% region of confidence or confidence interval. How do we make statements about it? That seems like we want to say something where it looks pretty. So let's make it look pretty. We are 95% confident that the true proportion of students who use Snapchat is between, I could say it two ways. I could say the decimal version, 0.51924 and 0.64076. Or I could say, I could finish that sentence with 51.924% and 64.076%. So I could finish it two ways. I think most people, when you're reading something, that the percentage makes more sense. While we're at it, I'm just going to calculate the confidence interval for the 90% and 99%. And I'll draw them right on the same graph. So let's come up here and draw them. Did I calculate these already? I did. I did the 90%. So if I do the 90%, I'm getting 0.5287 to 0.6313. Which is a narrower window. And if I do the other one, the 99%, let's go with maybe white. 99% was 0.4997 to 0.6603. That opens the window up, makes the interval larger. But we've taken enough samples that there's a good chance we're in there. Now notice, just like
We
when we
can't see
did,
the bottom.
oh,
Oh wait, never mind. I already wrote that down. Sorry.
okay. So like over here on my stat crunch, let me do it again. That's not what I wanted. Applets, confidence rules, or intervals, 0.58. We're gonna do 100. Ah, fuck it. Let's do 200. I was saying 0.58 is the exact amount. And this is, why are you not extending? There we go. Some of these include it. Some of them don't. So if I did a sample, like this was my sample, I didn't include the 0.58. The actual true proportion is a fixed thing. When we say we're 95% confident, we're just saying we're 95% sure that we got the right answer. We don't know if we've got the right answer or not. That's important to know. Okay, it's important to know the difference. So like if I wanted to put it in words, I thought maybe having that picture over there will help. Some of these samples contain it and some of them don't. The true value or proportion doesn't change like these windows do, these sample windows do. It doesn't change. Our confidence interval either contains it or it doesn't. There's no like we contain 95% of it. So 95% confidence interval is not saying we contain 95% of the answer. We either contain the answer or we don't contain the answer. The 95% is just how confident we are. And we're using that bell curve to come up with it. What else do I want to add this? So when we say 95% confident, means that 95 out of 100 samples will have that value. Contain that value. And thus it's likely that it's likely to be in there. Okay, so we never know the exact proportion unless we can ask everyone. That's important to know. And so when I was, maybe I should give you a second to write that before I continue. So I had that window, that interval up there. And what I did was I added 0.06076 that direction. And we subtracted the same thing to go the other direction. So this is like my point estimate. And if I call this E 0.06076, this value over here is like my point estimate minus the E. And this is my point estimate plus E. E is called the margin of error. And that's why we use it. Since P hat tends to be unlikely, our sample, our point estimate is unlikely to be the actual P. Highly unlikely. The true proportion. So we have a little cushion around it. Little cushion for error in our sample. Not well, the sample doesn't have error unless we fucked it up. A little cushion that our sample is off. And that would mean we were off. It's an error. That's why it's called the margin of error. Now, if you see problems, you might see problems that ask about this. They might say, well, they might reference the width. The width is 2 times that margin of error. Effectively, they're saying, how long is this distance? That distance is the width. And each of these distances was E. How many of you want to do this by hand? Anybody? Anybody want to keep doing this by hand? Who thinks calculating this by hand sucks? Are you? If you're not ready for me to go on and show the stack crunch approach, let me know. But it's important you know what all this shit means so that when you get stuff from stack crunch, you know what the hell we're talking about, right? As I hear no complaints, I will move on. So stack crunch. And we're going to go stats to proportion stats. This is the path we're going to take. For confidence intervals and hypothesis tests, which we will do after the confidence intervals. Chapters 10 through 13 are on hypothesis tests. Chapter 9 is on confidence intervals. So when we go in there, it's going to ask you some stuff. In fact, let's have that open at the same time and I'll show you. Stats, proportion, there we go. Stats, proportion, stats. First option, you are given the option of one sample or two samples. Now, a lot of the stuff you're doing is one sample. What I've been doing here is one sample. We will do two sample. It's usually when you're comparing two different groups and saying, do their proportions match up? Are they the same? Are these two groups equal? So that's what the two sample one is going to be. One sample is normal. Two samples a later chapter. I want to say it's chapter 12. It might be chapter 11. Chapter 10 is when we actually start diving into it. Then no matter which one we look at, you'll notice we have with data or with summary. They both say it, with data, with summary, and then power sample size. So next decision is data or summary. Data means you have the results in a column. Or two columns for two samples. I realize you can't see that right half of the screen. Let's move this over. And summary means you just have the compiled results like I gave you for Snapchat and we had it for COVID. You have N and P. Well, no, you have generally the number of successes and number total. It asks you for successes and observations is total. It doesn't default to saying confidence interval. It defaults to the hypothesis test. We come down here and we do the confidence interval there. Let's generate the one for our Snapchat that we talked about and see if our hand calculations match up with what StatCrunch gives us. Maybe let's look at a confidence interval plot. Let's see what it shows us for that. It gives us 0.518. I gotta scroll up. Look. I must have screwed up on my calculation up here somewhere. Oh, I rounded here. I used 0.031, not 0.0312. I didn't use the full thing, so I rounded there, and I probably shouldn't have. So it won't use that rounding, but it will come up with the lower limit and the upper limit. So those are what you're looking for when you see that. And it's giving you that window that we showed, like I was doing right here. It's doing that little confidence window like I showed it to. So that's all that does. The power sample size option. Stats, proportion stats, one sample power sample size. Power sample size and width sample size are pretty similar. We will use this to determine the N to use, N or sample size to use, so that we have bell curve results. We have normal results. Okay. And the computer is not going to do this for you. So actually, what did it give us here? I want to point out what it does give. Just had to open that up a little bit. There you go. You can see it again. It'll give us our margin of error. This is our margin of error right here. The standard error is the margin of error. That's our E. That 0.0312 is our E. But it doesn't, it tells us, well, and then that's our standard deviation. So it will give us, StatCrunch will give us it yields our mu, which it calls sample prop or sample proportion. And it gives us sigma, which it lists as standard error. No, that is not sigma. Yeah, that is sigma. That's standard error. That's our sigma. That's not the margin of error. The margin of error was 0.06. Okay, that's what it gives us. It doesn't confirm that it's what we want, that it meets the criteria. And recall the criteria is N times P times 1 minus P is greater than or equal to 10, and N is less than 5% of the population. We can do that on our proportion, our Snapchat. Let's just check that on our Snapchat. I didn't do it for our Snapchat. Maybe I should have. N was 250 and P was 0.58. So I've got 250 times 0.58 times 1 minus 0.58. Is that greater than or equal to 10? I don't know. I made a lot of assumptions that it was, but did I check it? Nope, because I'm a lop of a teacher. But it is. This is 60.9, which is in fact greater than or equal to 10. And I can guarantee you with beyond a shadow of a doubt that 250 students is less than 5% of all students that use Snapchat. How do I know? There's millions of students in the United States. There's no way 250 is not 5%. So it meets that one. Let's look at some examples. I'll let you finish writing that, and then we'll look at some examples from the homework. Ooh, from the homework, he says. Say what? All right, gonna maximize this window over here. We're gonna go over StatCrunch. That's not where we were. We were in the homework. I don't know, let's take a look at question 3. It says determine the, enlarge it for people watching the video at home. That might be too big. Determine the point estimate of the population proportion, the margin of error for the following confidence interval, and the number of individuals in the sample with a specified characteristic X for the sample provided. So it's got those numbers. I'm going to write them down on my notepad before I shift over to it, and we can talk about that calculation. You will have different numbers. My lower bound or lower limit is 0.369. My upper bound, which is another way of saying upper limit, is 0.771. And I have n equals 1500. And they want the point estimate. And they want the margin of error. And round to the nearest thousandth. That's important. Thousandth. So I will come back over to my other window and we'll go look at that stuff. I got it right here. So I got this window. How can I figure out what that point estimate is? We know, like if I draw this lower bound and upper bound, this 0.369 is over here. This upper bound is over here, 0.771. And we know from the pictures we were doing earlier, the point estimate is exactly halfway between it. Halfway. And that this distance is the margin of error. Well, one way I think that's more intuitive than the other would be, well, let's calculate the width. Because we know width is 2 times the margin of error. And that means if we have the width, the error is the width divided by 2. And once I have that error, if I start at the lower bound and add E, I should get to P hat. So the width is just subtraction. .771 minus that 0.369. Let's do this without a calculator. Ooh, without a calculator. That's a 2, that's a 0, that's a 4. My width is 0.402, which means my margin of error is 0.402 divided by 2 is 0.201. If I start at my lower bound and add E, I've got 0.369. I'll do addition just like I would normally, add them vertically. 0, carry the 1, 7, 5. That should be my P hat, which is 0.570. So I'm going to come over here and enter that. The number of individuals in the sample with the specified characteristic. So if we know the proportion, how do we figure this out? We're trying to find X. We have, remember, X over N equals P hat. I know what P hat is. I know this value. And I know this value. If I multiply both sides by N, I get X equals N times P. And we've done that before. We've done that before in a lot. Oh, I'm off screen. We've done N times P. Whenever it goes, what's your proportion? And then they go, okay, if we did this 1,000 times, how many could we expect to see? MATLAB loves doing this. It has you do this, take the sample size and multiply by P. And it's having us do it again. What was our sample size here? 1,500. 1,500 times our 0.570. That's our N times P. And I'm getting 855. N times P should almost always, this should always be a whole number. If you do your calculation and you get like 855.5, something's wrong somewhere. Well, that's not true. You generally have to round to the nearest interval. Usually that's proportion is usually rounded. They round to the nearest thousandths or whatever, so it might be off. In this case, it was. So maybe I'm going to take that off. That's not true. But what you enter should always be rounded to the whole number. In this case, it's just the 855, and we're going to go with it. I can't see it anymore. There we go. In fact, it tells you round to the nearest integer. See that bad boy? Round to the nearest integer. Okay, let's look at another question. Let's go to like question 6. And I'll put it in the center of the screen. And it says a survey of 950 adults. So let me write on this while I'm doing it. I'm taking notes while I read it. A survey of 2,295 adults. I do not know why I said 950. I'm sure I said that out loud. That's got to be my N, right? Right away, it's telling me how many N is. A survey of 2,295 adults in a certain large country, age 18 and older, conducted by a reputable polling organization, found that 409, that's going to be my successes, have donated blood in the past few years. You do not need this standard normal distribution table. This is for when you're doing it by hand. We are not going to use that. We will use StatCrunch for this. Don't use the tables. Use StatCrunch. And the first thing they want is p hat to 3 decimal places. What's going on? Oops. Really? I was doing the damn problem and it fucking logged me out, you piece of shit. All right, I'm logged back in. Hopefully it'll allow me to just keep going. All right, let's do that over here. We're going to do stats, proportion stats, one sample with summary. Because they didn't give me the actual data, they gave me a summary. So that's where I'm going to enter it. Oh, wait, not for p hat. I can just do p hat by hand. What am I doing? P hat is x over n. StatCrunch will give it to us. But you should be able to know how to do this by hand too. At least the getting p hat. To 3 decimal places is 0.178. Let's confirm that over here. Stats, proportion stats, one sample with summary. I've got 409 successes, 2295 observations. I don't know what confidence interval they're going to have us check. Let's leave it at 95 for now. I'll click compute. That sample proportion is what that p hat is. And to 3 decimal places, it's 0.178. So I got that either way. We'll hit enter. All right, this one I can't write out. Let's see. It's asking for verify the requirements. So we can do this by hand and then figure out what we need to put in the window. So we're verifying the requirements. The requirements were, if you recall, n times p times 1 minus p is greater than or equal to 10, and n is less than 0.05 of the population. Now it says of a large country, adults in a large country, so I got to assume that 2,295 is less than 5%. I'm going to make an assumption there. That seems like a reasonable assumption. For this one, though, we actually have to calculate it. So we got 2295. We're going to multiply that by 0.178, and then 1 minus 0.178. .178, then times 2295. And I'm getting, I don't know how many decimal places they want. I'm sure they're going to make me report this though. So I'm going to write everything down on my calculator. That is greater than 10. That's greater than 10. So that's met. That's a check mark right there. That's met. Now let's just take a look and see how they want us to enter that. The sample, is it stated to be a simple random sample? It's not. It doesn't state it, but it's conducted by a reputable polling organization. And if they're reputable, we got to assume they did a simple random sample. So I think we can assume that. And then they say the value of, this is what we want, n times p times 1 minus p. And they want it rounded to 3 decimal places. 3 decimal places would be 33.5795, which is 33.580. So 33.580 is to 3 decimal places. Yes, there it is. Which is greater than or equal to 10. And then we wanted the sample size to be less than . We can assume it to be, since it's the country is large, is less than or equal to 5% of the population size. So assuming I did this calculation over here on the left correctly, That should work. Oh, you sons of bitches. Did I do my calculation wrong? I rounded to 0.178. Maybe I won't round here. So let me write some more numbers down. 213,507. Let me use that number. Maybe my rounding there gave me something wrong. So I'm going to put that in here and in here, and I'm going to recalculate. Well, that's a lot different. I must have done something wrong earlier. I'm getting 43.204 now. That does not explain the decimals. I must have entered n wrong. So let's try that. Let me do this again. I've got 409. It is 409. Yeah, 409 divided by 2295. That's my P. Oops. And then I want to multiply that times n. And then 1 minus that number. Yeah, 43.204. Look at that. I done had the wrong thing. Shit. I put the wrong number. I calculated it wrong. UMFer. Okay, let me use the 0.178 again. Let's go back to 0.178. This is the trial and error that you must do. Don't just assume you're wrong. Like I know what I'm doing. I know I'm just doing something wrong in the calculator. So let's just go back to that. Times 0.178 times 1 minus 0.178 in parentheses equals, Jesus, that's a big number too. Now I'm getting 335.79. What is going on? Fuck that calculator. Let's use my cell phone. Do it 6 different times, get 6 different answers. I'm doing something absolutely ridiculous. Yep, I had the decimal place wrong. I don't know what I was getting with the 42. I got a 43 there. All right, let's try this again. 335.795. I swear to God, I know what I'm doing. I really do. There we go. There we go. All right, so that's a pretty good lesson. And don't give up. Don't just assume you're wrong. In general knowledge, if it tells you you're wrong, good chance you made a calculation. Oh, not done. Construct and interpret a 90% confidence interval. Okay, this is where we're going. Stat crunch. 90%. I had 95 there. I want to change this to 90%. So 0.90 confidence interval. I click compute. And to 3 decimal places. I want the lower limit is 0.165. The upper limit is 0.19 what? So there is a 90% probability. That's not what we want. That's not right at all. We are 90% confident. It's not a probability, it's a confidence level. We are 90% confident that the proportion of adults in the country that blah, 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 blah is 0.165 and 0.191. There we go. All right. So that's going to be it for today. On Wednesday, we're going to do 9.2. 9.2 is on doing the same thing for a population mean. And I think I'll get a width sample size or power width sample size in there for that one as well, just to give you a sample of what you can expect on your homework. But I think we're going to call that a wrap. Any questions? All right. I'll catch you guys later.
Have a good day, Professor Jones.
You too.